Hello, I am Arjit Jain. I'll be presenting our work ExGAN, Adversarial Generation of Extreme Samples. We start by looking at this picture. On the left, we have existing GAN-based approaches which try to fit the bulk of the data. They tend to generate typical data samples, and this is shown here by rainfall patterns which have low to moderate rainfall. On the right, we have our approach ExGAN, which tries to fit the extreme tail of the data distribution. It generates extreme samples with varying severity. This is shown here by extreme rainfall with spatial patterns resembling real floods. We now describe our motivation. We want to model extreme events in order to evaluate and mitigate their risk. This has applications in extreme weather events, financial crashes, and managing unexpectedly high demand for online services. For this, we need to be able to generate a wide range of extreme scenarios. This can be used by domain experts to understand the nature of extreme events. This can also be used to perform stress testing to ensure the system remains stable under a wide range of extreme but realistic scenarios. So now we have a rough problem statement, that is, how can we generate a wide range of extreme but realistic scenarios. We are immediately faced with the question, what does it mean to be extreme and how do we measure extremeness? Well, the short answer is it depends on our end goal. Let's take a few examples to understand this. In a database management setting, a typical end goal is resilience against high query loads. Here, an extremeness measure could be the number of queries per second. This means we will want to generate rapidly arriving queries with realistic access patterns. Another example could be in rainfall analysis. Here, one end goal can be to gain information about severe floods. The extremeness measure could be the total rainfall. That means we will want to generate high severity floods with realistic rainfall patterns. We continue with our rainfall analogy. In hydrology, a 100-year flood is defined as a flood that has a 1 in 100 chance of being exceeded in any given year. In a similar way, for condition generation, we can define an extremeness probability tau, which represents how extreme the user wants their sample data to be. For example, tau equal to 0.01 represents generating an event whose extremeness measure is only exceeded 1% of the time. We now have the tools to define the problem statement formally. We are given a training dataset x1 to xn sampled from an unknown distribution T, a user-defined extremeness measure E of x, and a user-specified extremeness probability tau in 0 and 1. With this, we want to generate samples x prime that are 1. Realistic, that is, they are hard to distinguish from the training data, and 2. Extreme at the given level, that is, the probability that the extremeness measure of a randomly drawn sample from the distribution exceeds that of x prime is as close as possible to tau. The first challenge that we face is the lack of training examples. In any moderately sized dataset, the rarity of extreme samples would mean that it is typically infeasible to train a generative model like GANs only on these extreme samples. The second challenge is conditional generation. That is, we need to be able to generate extreme samples at any given user-specified extremeness probability. We now describe our two-step approach. The first step is distribution shifting. Here, we gradually shift the data distribution in the direction of increasing extremeness. This allows us to fit a GAN in a robust and stable manner while fitting the tail of the distribution rather than the bulk. The second step is EBT based conditional generation. Here we train a conditional GAN which is conditioned on the extremeness measure. We then use EBT analysis along with keeping track of the amount of distribution shifting that has been performed to generate new samples at the given extremeness probability. The first step in the distribution shifting algorithm is to sort the dataset, here shown by blue samples, in decreasing order of extremeness. Here we are assuming that the height of each sample is proportional to its extremeness measure E. The next step is to create a shifted dataset. We initialize the shifted dataset, here shown by green samples, to be the same as the input dataset. We then begin the shifting for loop. In each iteration, we train a GAN on the shifted dataset. We then replace the shifted dataset with a fraction of the top extreme data points from the input dataset. Next, we use the GAN to generate additional samples, here shown by the red samples, and add a fraction of the most extreme samples to the shifted dataset. The number of data points that are generated and retained are as shown in the slide. These numbers are a function of the shift parameter C, the size of the input dataset N, and the iteration number I, and they ensure that the shifted dataset is brought back to its original size. Before we describe the next step of our approach, we give an extremely brief primer on extreme value theory. We first discuss the generalized Pareto distribution. The parameters of GPD are its scale and shape. The CDF, or the cumulative distribution function of GPD, is as shown in the slide. We now describe the peaks over threshold method. A theorem in EVT states that the excess over a sufficiently large threshold U, denoted by x minus u, where x is the random variable, is likely to follow a generalized Pareto distribution with the parameters sigma u and xi. This means the scale is a function of the threshold. In practice, the threshold u is set to a value around the 95th percentile. In the next step of our approach, that is EVT based conditional generation, we first calculate the adjusted extremeness probability. After k shifts with the shift parameter c, the adjusted extremeness probability tau prime becomes tau divided by c power k. Then, for each data point in our shifted dataset, we compute the extremeness values. On these values, we can then apply peaks over threshold method and estimate the GPD parameters. We then train a conditional GAN on the shifted dataset, where the conditioning input for the generator is sampled from the GPD. In addition to the data sample, the discriminator takes in a second input. For fake data, this is the conditioning input that was fed to the generator, whereas for real data, it is their respective extremeness measures. We also add an additional loss to the GAN objective as shown in the slide. This helps reinforce the conditional generation probability and prevents the generation of samples with unrelated extremeness. Finally, we use the inverse CDF of the GPD to determine an extremeness level E prime corresponding to the adjusted extremeness probability tau prime. Then we sample from the generator using this extremeness level. We now describe the baseline approach against which we compare our approach. The baseline is a DC GAN trained over all images in the dataset combined with rejection sampling. We use EVT as in our framework to compute the extremeness level corresponding to the extremeness probability tau. We then repeatedly generate images until one is found that satisfies the extremeness criterion within 10% error, that is, we reject the image X if the condition on the slide holds. We use the US daily precipitation dataset, which records the amount of rainfall over a spatial grid. For training, we use the data from the duration 2010 to 2016, whereas for testing, we use extreme data samples in the duration 2017 to August 2020. Here are normal examples from the dataset, and here are extreme examples from the dataset. We now show ExGAN generated samples on different extremeness probabilities. Here are the samples at tau equal to 10 power minus 3. These are some samples at tau equal to 10 power minus 4. Our first evaluation metric is the Frischer inception distance, but an ImageNet pre-trained inception network is not suitable for our task. Hence, we train an autoencoder on the test data. We use the statistics on its bottleneck activations to compute the Frischer distance. Our second metric is the reconstruction loss. Here, we try to reconstruct the test data by optimizing over the latent space vectors using gradient descent. We see that in both those metrics, ExGAN outperforms the baseline. Finally, we look at the sampling times. We report the time taken to generate 100 samples for different extremeness probabilities. The baseline could not generate even one sample for the extremeness probabilities tau equal to 10 power minus 3 and tau equal to 10 power minus 4 in 1 hour. On the other hand, ExGAN is scalable and generates extreme samples in constant time. In conclusion, we proposed a novel deep learning based approach for generating extreme data using distribution shifting and EVT analysis. We demonstrated how our approach is scalable and able to generate extreme samples in constant time. Our experimental results show that ExGAN generates realistic samples based on both visual inspection and quantitative metrics. Our paper can be found at the given archive link, and our code and datasets can be found in the given GitHub repository.